Hi, and welcome to today's presentation on behavior model for automated driving. My name is Thomas, and I'm a technical product manager for PTV Vissim. Automated driving has become a recurring, or you could also call it maybe a steady topic that keeps the mobility industry quite busy. The number of requests on simulation studies that deal with the impact of automated vehicles is growing. Up until now, we provided some specifically tweaked driving behaviors that mimic the behavior of automated vehicles. However, in their core, these models are designed to represent human behavior, so simply tweaking these to reflect something else naturally has some shortcomings. Therefore, over the last months, we implemented a new car falling model and a new lane change model, both modeling the behavior, so to speak, of automated vehicles. And today, my goal is to briefly outline how those models work, how they can be combined, what their objectives are, and what you have to consider when using them in Vissim.
Let's start with a brief overview of the presentation. First, I'd like to recap the previous implementation, well, in quotation marks, because so far these have not been real implementations, but like I just mentioned, rather tweaked existing driving behaviors. Next, I'll introduce the new behavior models. This time the quotation marks are there because I find it a bit strange to talk about behavior when we describe what an automated system is doing. I'll briefly outline what these models do and how they work using some slides, and then I'll transition to Vissim to show you how they are configured, what are the most important aspects to keep in mind when creating models using these new models, and obviously I'll also run a simulation to show the automated vehicles in action. Well, and finally, I'd like to recap the most important aspects that you should consider when using these models in the future, and afterwards I'll be available to answer some questions. So let's start with the previous implementations. You might be well aware that there are already 3 different driving behaviors in Vissim which are labeled AV, cautious, normal, and aggressive. And as the names indicate, these originate from the Coexist research project. As you can also see, these driving behaviors use the normal car falling models, specifically Wiedemann 99. However, they are calibrated based on empirical data of AVs so that they reproduce this behavior of the AVs. And in a sense, they are trimmed or truncated so that stochastic effects are reduced, but the underlying model is still the same, and that one has been designed to reproduce human behavior. And that limitation is something that the new developments address. Well, therefore, let's dig into these models in the next couple of slides. What we introduced are basically 2 models that allow to model different levels of automated driving. The first one is a new car falling model that you can select in the driving behavior settings for the car falling model. It's called ACC, which is short for Adaptive Cruise Control. And this following model can be combined with all the normal models, parameters, and settings for human drivers to reflect, for example, how human drivers behave using an ACC on a highway. The second ingredient is a specifically designed lane change model, short ALC for automatic lane change, which the next service pack will allow you to simply activate using a checkbox in the lane change tab of the driving behavior settings. The model and the checkbox will be available with the next service pack, and I apologize here for the, let's call it, almost done screenshot with the internal label, and I promise that that one will change to automatic lane change. Well, and in combination, these 2 models can mimic the behavior of high-level automated vehicles, for which you have even a bit more freedom using different parameters in the model itself. But before I'm going to tell you about that, a brief wrap-up of how these models work. The ACC has a bunch of parameters. We provide suitable default settings, so you don't have to worry about all of these if you do not want to, but you can if they are, let's say, the subject of your specific study or project. The default parameters reflect rather cautious nowadays behavior of AVs, which goes in line with current regulations that AVs have to fulfill, and among many other things, considers time gaps and decelerations of the own and neighboring vehicles. On a side note, with the release of Vissim 2025, these parameters have only been available in the list of the parameters for the driving behavior, and we only just now added these to the dialog, as you can see it here. The model itself consists of three, let's say, core parts. The first one is the following time gap controller, which controls the vehicle's acceleration while following a leading vehicle, and tries to maintain a specific minimum gap time, which is one of the important parameters that you should be aware of. The other one being the standstill distance, which does exactly what the name tells you and is also considered in the minimum gap time that the controller tries to maintain. The second component is the target braking controller, which basically kicks in when following fails. For example, if the AV has to come to a stop before a traffic light, or more likely before another vehicle. And for example, specifically if someone cuts in right in front of the AV on a highway, for example. The third component is a jerk limitation, which is applied well in general and very specifically for transitions between the different controllers. For example, when a new lead vehicle is detected and another controller kicks in. Well, and below you probably already observed the animation, which shows Wiedemann 74 vehicles and ACC kind of next to each other. Admittedly, the differences are hard to tell, but what you might be able to observe is that the ACC controlled vehicles are more regular and stable in terms of the distances and the gaps that they maintain. And this stability can even be explained if we look at the typical approach and the different states of a vehicle approaching a slower driving lead vehicle. And while far away, a faster vehicle is in, well, free driving mode and simply closes the gap to the lead vehicle. And well, when it gets close enough, it brakes and decelerates slightly until it enters the following state, the state which, well, as imperfect as we humans are, ends in the hopefully well-known oscillating following behavior, where we ever accelerate and decelerate slightly, trying to maintain a constant distance to the lead vehicle, but we ultimately fail in doing so because of misperceived speeds, misperceived distances, and where we are not super aware of what our foot exactly does to the pedal and the acceleration, and that's why we'll keep oscillating. Well, in contrast to that, a machine is a bit more predictable, and the following behavior looks like this, where after the approaching state, a faster ACC-controlled vehicle basically hits the perfect distance and is also able to maintain that distance, given that the lead vehicle is driving at a constant speed. And well, that is basically the core difference between these models, which different parameter sets for Wiedemann 99 can reduce, like it has been done for the Coexist project, but it's always somewhat part of the system, and that is new and different for a dedicated ACC controller. Okay, let's move on to the new lane change model for automated vehicles. Like mentioned earlier, this model can be activated using a checkbox. And well, and let's dig into what the model does, or the different stages it consists of, which are basically 3 different stages. In the first one, the ego vehicle, which you can also see here, detects a desire to change lane, because for some reasons it's more beneficial to change lanes. Most of the time this will be because the lead vehicle is slower than the ego's vehicle desired speed. Well, and then if a vehicle wants to change, it tries to look for a safe opportunity to start the actual lane change maneuver. Here it considers the neighboring vehicles, very importantly the following vehicle on the target lane, its distance and speed, its own speed and distance to the lead vehicle, the decelerations that anyone has to experience in case of changing or not changing the lane, and again, here the default parameters that we'll ship have been calculated so that current regulations for AVs are fulfilled. Well, and finally, if there's a desire and a safe opportunity for a lane change, the lane change maneuver execution starts, which basically describes, well, the literal transition, switching from one lane to the other, considering the time for a lane change and all that stuff, so that it finally moves on to the next lane. That's roughly the different stages for the automatic lane change. All right, enough slides. Let's take a look at Vissim. What you see here is a simple highway test model. It's about 3.5 kilometers long, and it has everything that is required, well, to simply test things and see if things work properly. It consists of an off-ramp and an on-ramp, and well, I'll briefly walk you through the most important aspects. And I'd start with taking a look at the driving behaviors. We can see here the name indicates that this one is supposed to describe what automated vehicles do. If we look at the settings, we see that for the car following model, the adaptive cruise control with all its parameters is chosen. This one is simply another option in the list of the different car following models. Like mentioned earlier, the most important ones are the minimum gap time and the standstill distance, and you can feel safe using the default parameters for the others. Now, the other component to describe a high level of automation is the lane change. And well, like mentioned earlier, here's this checkbox, which allows you to activate the automatic lane change. One thing to keep in mind here is that this one can only be combined with the ACC car following model. So, for example, if I switch that one to one of the human driving behaviors, this one will be grayed out, indicating that the lane change is not applicable on its own for automatic vehicles, but rather in combination with the ACC car following model. What you can also see here, and that's kind of a common theme when it comes to modeling automatic vehicles, is that there is a lane change duration distribution set here for the automatic vehicles, and this one is basically not a distribution, and that's the common theme that I was thinking about. And let's simply take a look at how this time distribution looks like. It's 3.6 seconds, and as we can see, it's basically not a distribution, but there are constant values. So all the vehicles using this time distribution will take the same time for a lane change. This theme is also applied for desired speed distributions, basically reflecting the fact that the automatic vehicles do not choose these parameters on personal preference, but are rather hard-coded. And that's one thing to reflect also the differences of how automated vehicles behave when using them in models. All right, in terms of applying them to the model, like mentioned earlier, it's a highway model, and you can see that I use linked behavior types to map this specific driving behavior to specific vehicle classes, so that they use the different driving behaviors. There's a small difference between the highway and the off and the on-ramp. Furthermore, this is not relevant for the results, but it helps understand what's going on. I use different colors for the different car types. This model is also limited to just cars, so no HGVs or LGVs. And well, I use the black color for cars which are human-driven, and the red color for cars that use the automated behavior models. Another thing to keep in mind, this goes back to the automatic lane change, and is an attribute which is new for links, which has to be considered. The lane change of automated vehicles is done in a way that one has to keep in mind that automated vehicles are, let's say, afraid of what they do not know. Again, that's a bit of the cautious aspect that is typically observed or connected with these kind of vehicles. So if a vehicle using the automatic lane change considers trying to find an opportunity for applying a lane change, it assumes that just outside of its lookback distance, which represents the detector range, there is a vehicle upstream which goes at a specific speed limit, and it has to assume that this is just outside of its detection range and has to consider the potential presence of such a vehicle when considering to go for a lane change maneuver or not. So that's for safety aspects. And the base speed of this vehicle that just might be there is defined by a link attribute. The link attribute ALC V limit is basically providing this baseline worst case speed for an automatic vehicle when it tries to consider doing or not doing a lane change. So another thing that one has to keep in mind when it's about modeling automated vehicles, again, expert interviews that we made led to the conclusion that these are typically more cautious. And one thing here to keep in mind is that, first of all, the automatic lane change that we implemented is only there for free lane changes, so the ones that apply when I want to change the lane because I'm not able to drive, for example, at my desired speed. But if I have a necessary lane change, which is required, for example, to follow a route, in this network, for example, when I need to get the lane that leads me to this off-ramp. And here, now going back, AVs are typically more cautious, and one way to reflect this is to apply a longer lane change distance for vehicles of that specific vehicle class. And as a rule of thumb is that you can go with twice the amount of lane change distance that you would apply for human drivers. And again, here, a specific distribution, which again is actually a constant value, is used to model the impact of this more cautious behavior with respect to necessary lane changes. Well, okay, that's basically the most important aspects that we have. Maybe highlighting again the distribution aspect. I also used desired speed distributions. Here the ones, the default ones, 90 and 130 kilometers for human vehicles, which try to reflect what all we do. We do not obey all the rules. So basically, even though it's labeled with 130 kilometers, you know that there will be a bunch of vehicles that actually go faster. And this is something that won't be the case for automated vehicles. And that's why here I created desired speed distributions, again in quotation marks, because actually it's just a constant value that reflects that these vehicles will simply obey to the rules. So, well, enough going through some parameters and dialogues. Let's simply start the simulation and see how this works out in action. And well, you see that's a simple mixture of AVs and normal vehicles. And again, it's a bit tricky or difficult to observe in the simulation the difference with respect to the specific vehicles. However, what you can in general observe is that they are more cautious, the red vehicles, and that these have an impact on aggregated numbers if you run many simulation runs and look at the, let's say, the macro values of the results. Well, all right, that's briefly describing how this works in Vissim. So let's go back to the slides. And I would, well, simply recap the most important things for modeling models with the new AV behaviors. So let's recap these. There are two new models, one for the car following and one for the lane change. And you can combine these for high-level automated vehicles or use just ACC for humans using an ACC. Use desired speed distributions for AVs, which, well, are not distributions, but rather take away the randomness because automatic vehicles will obey the rules. The automatic lane change is only applied for free lane changes, so mostly on highways, and AVs are afraid of unknown vehicles just outside of their look-back distance, and they assume worst-case speeders and therefore might not overtake. And the link attribute ALC V limits specifies the base speed of the link that an AV considers for this, and it adds its own behaviors attribute ALC delta V limit on top of that. A different behavior for necessary lane changes can be applied using longer lane change distances, and this is in line with what experts told us about AVs and that these will be more cautious than human drivers. And well, in general, the default settings will be nowadays cautious AVs and specifically fulfill the constraints of the UN regulation 157. And well, if you're interested in details, you can check out the source provided here at the bottom. And well, also in general, more futuristic, bolder AVs are kind of a black box. You can use shorter gap times, higher speeds, or in general, let's say more aggressive numbers for decelerations and many other things to make them more bold. So finally, when and where can you use these new models? Well, the ACC is already included in Vissim 2025. And like mentioned earlier, the graphical user interface for the driving behaviors will only be added just now. And the ALC will be included in one of the next service packs, which will likely be released in March.
All right, this brings me to the end of this presentation. And I'd like to conclude with a summary of what I've just shown. There's a new car following model called adaptive cruise control, which can be used to model the impact of humans using an ACC. Furthermore, there's a new model for automatic lane changes, and in combination, both models reflect the behavior of high-level automated vehicles. Desired speed distributions and a few other things should be used in a Vissim model in order to consider automated vehicles in a comprehensive way. The ACC car following model is already available in Vissim 2025, and the lane change model will very likely be added with the next service pack. If you have questions right now, I'd be happy to answer them right away. And if questions pop up later, please contact PTV using the support channels. The only thing left to say is thanks for watching this session. And I'd like to point out that there are still a few more to come as part of the in-depth series of the Mobility Tech Update.